Good morning, all. Happy to see you here. Beautiful day outside. If you're in Orlando area, make sure to get out today away from the computer for a walk or for a run. If you have a pet, spend some quality time with your pet outside because it's beautiful. It has not been that beautiful for the past couple of days, and it's a nice change. All right, are there any questions before I start the lecture? All right. So a couple of reminders, as per usual. Quiz 9 is due today. Today is Wednesday, and quiz 9 is due today. Quiz 10 opens tomorrow, and it's going to be due next Wednesday on March 31st. Okay, so, I can see a question from Lily in the chat. During the last lecture, you said that we would have the final before spring break, but in web courses it says we're having it's not going to be a final, Lily. It's going to be the exam number 3. Okay, final is the final exam. Final exam stands separately. I meant the last exam out of 3 exams during the course. Final is happening on April 30th as per schedule. Okay. All right, back to quizzes, back to the reminders. Quiz 10 is again opens tomorrow and is going to be due on next Wednesday, March 31st. And participation assignment, we have a short one for today, and it's due before midnight tonight. So 11:59 p.m. is the last time that you can submit. All right, I'm going to finish up the populations lecture that we started yesterday, and I'm going to start incorporating some global change aspects of how humans influence various aspects of ecology. Okay, because we likely won't have time for the global ecology lecture, so instead of doing the whole lecture on global ecology, I'm going to start incorporating pieces into the lectures on population, on biomes, biodiversity, and so on. Okay, so last time on Monday, we finished at looking at life strategies of various species or various groups of organisms, various populations, I should say. So we took a look. We looked at the survivorship tables, survivorship tables, and we looked at the survivorship curves over age. And from there, we found out that there are 3 types of survivorship curves: type 1, type 2, and type 3. Type 1 curve is characteristic for species that look after their young and have very few offspring. They don't reproduce very often. And the type 1 survivorship curve basically characterizes the population where most of their young survive, and the population starts dropping off when the individuals reach the older age. So most of the individuals within a population die from old age. Okay, this is type 1 curve. In type 2 curve, the mortality rate is pretty uniform over the course of the age of the individual. So type 2 curve is very characteristic for birds, various species and populations of birds. And finally, type 3 survivorship curve is characteristics for populations who do not look after their young and produce a lot of offspring. Okay, so next I'm going to revise what are the life history. So there are 2 life history: opportunistic and equilibrium life history. And you'll notice that I gave you points for question number 3 in the participation assignments for Monday, because we didn't really get to equilibrium life history, and it would be unfair to ask that question of you. So everybody got credit for that. So life history. There are 2 types of life history: opportunistic and equilibrium. Opportunistic life history is characteristic for species with type 3 survivorship curve. So like fruit fly is an example of that. Some weeds are an example of that. Lots of insects, I want to say all of the insects, have opportunistic life history. So the survivorship curve is a kind of negative exponential looking, negative power kind of curve. And it's basically says that a lot of individuals do not survive to the age of reproduction. So the individuals that are able to reproduce produce a lot of offspring, but they do not look after them and kind of leave it up to chance for the babies to survive. And as a result, lots of babies die and very few survive to reproductive age. But those few that do survive to reproductive age, again, produce a lot of offspring. And because of this overproduction of offspring, the populations are able to stay stable or even increase. Populations of the organisms that have opportunistic life history. So here are the properties that are characteristic for opportunistic life history. So there's high reproduction rate that I've covered extensively. There are many offspring. Each offspring receives little parental care. There is low survival rates for juveniles and early reproductive maturity, and type 3 survivorship curve. Okay. So the equilibrium life history is kind of the opposite of the opportunistic life history. In the species and populations that have equilibrium life history, they allocate more energy to ensuring the survival of the offspring. So instead of allocating energy to producing many offspring and leaving it up to chance for the offspring to survive, the populations with equilibrium life history, they are allocating more energy to taking care of the young, or if it's some plants have also equilibrium life history, and the plants obviously cannot take care of their young, but the plants allocate energy to ensuring the seed has a high probability of survival and germination. Okay. Uh, the characteristics of the equilibrium life history are low reproduction rates, few offspring. Each offspring receives extensive parental care. There's high survival rate for juveniles. There's late reproductive maturity, and the individuals with or species with equilibrium life histories have type 1 survivorship curve. Okay, so the examples of the book gives an example of an elephant. Elephants have very few offspring, and they take care of them for a long time after they're born, ensuring their survival. Bears have equilibrium life history. Us humans have equilibrium life history. And among plants, the good example of a plant with equilibrium life history is coconut. So coconut does not produce a lot of offspring. It doesn't produce a lot of coconuts, but each coconut has lots and lots of energy stored in it, like the nutrients to support the germination and early survival of the offspring of the coconut plant. So coconuts can survive a lot of conditions, okay? Even if the area gets flooded, maybe the sea level rises, and the coconut can swim in the sea for a long time, and after it just kind of beaches somewhere, it can sprout, and still this offspring can be successful in surviving. I see the question from Joshua: would turtles fall into equilibrium or opportunistic? Good question, Joshua. So turtles, they lay a lot of eggs, and they do not take care of their young. So lots of baby turtles, they hatch from the eggs, but not many survive. So I would put it into opportunistic life strategy, because turtles, they do not take care of their young. They kind of leave it up to chance for the baby turtles to survive. Uh, yeah, and very few of them do, actually. If you're interested in turtles, by the way, check out Kate Mansfield's lab in our Department of Biology. She does a lot of exciting research, and she actually works on answering these questions, just how many baby turtles survive to the reproductive age. But yeah, turtles lay a lot of eggs, and there are a lot of those eggs are hatching. And if you are at the beach at the time of the when baby turtles crawl out, there's a lot of them coming out of one nest, and not many of them survive. So that would put them into opportunistics. Ba, 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 ba. All right, what else did I want to say about this? So, are the differences between equilibrium life history and opportunistic life history pretty clear to you guys? Great. Uh, if you covered this kind of stuff in grade school, you might have heard of the term K strategist and R strategist. So R strategists are basically the synonym to opportunistic life history, and K strategists is the synonym to equilibrium life histories. Lauren asks, so type 2 would not be equilibrium. So type 2 could be equilibrium. It's type 2, the species with type 2 survivorship curve, they can be equilibrium or opportunistic. Um, mm, mm, mm. Or even in between. I'm thinking of birds, and let's say if we take an example of purple martin bird, they take good care of their young. So I would put them at equilibrium life strategies. They don't produce a lot of offspring, and not they don't not like insects, for instance. And they do take care of their young very well. So I would put them at equilibrium life history, even though they have type 2 survivorship curve. So type 2 survivorship curve basically it characterizes the mortality. Okay, it doesn't necessarily characterize how um, how well the parents take care of their young. So mortality in type 2 survivorship curve, the mortality rate or the probability of mortality is the same for individual at any age. All right. Now, next I want to talk about the kind of growth patterns that populations may have. There are basically two types of growth patterns. The population growth can be exponential or it can be logistic. So when we look at the change in population size over time, uh, this curve, take a look at this curve. So the x-axis here is time, the y-axis is the population size, and over time we can see this kind of curve. And this kind of curve, the J-shaped curve, is called an exponential curve. Um, and the second type is called the logistic curve. So in logistic curve, there is a phase of exponential growth. So there is a portion of the curve that is kind of the same between the green colored curve and the yellow kind of curve. But over time, in the logistic growth, the population kind of levels off at some level. So this level at which the population doesn't grow anymore, the level after which at which population remains stable is called carrying capacity. Okay, and this carrying capacity is the population size that the environment is able to maintain, sustainably maintain. Okay, why there is carrying capacity? Because as the population grows, the competition between between individuals within a population increases. The competition for resources, the competitions for mates, and what else? The the rates of diseases increases because the more dense is the population, the better chance that the disease will spread more easily among the individuals. So if the population is sparse, one individual may get sick and die, but because population is sparse and there is little contact in between individuals per given unit of time, the disease will just not spread. The individual will die, and that'll be it. But if the population is very dense, then there is more social contact between the individuals within the population, and diseases spread more easily if it's a communicable disease. Also, as the population density increases, there is increased rate of predation. So picture, um, I don't know, what is a good example? Lions and zebras, okay? If zebra population is very dense, it's easier for lions to hunt them. But if zebra population is sparse, there's less probability that the lion will be successful in getting a zebra, in eating a zebra. Okay. So there are two types of age structures that are characteristic for logistic and exponential growth, but because there's no axis here, it's hard to say what those age structures mean. But we will see them again, and I will go over them in detail later. So what questions do you have about the differences between exponential growth and logistic growth? Have you guys studied that before? Is it a familiar topic? From Melis, I'm going to cover the age structure a couple of slides from now, okay? There is no x-axis here, so it's kind of hard to tell uh, what those bars represent. Okay, Samir asks, does exponential growth continue past the carrying capacity? Great question. So if there is carrying capacity for a given population, the exponential growth will eventually cease to exist because the population will level off at carrying capacity. But if there's no limits in space, if there's no predators, if there are enough resources to support some indefinite growth of the population, then exponential growth will continue. But in reality, there's always something that limits exponential growth. So exponential growth is rarely observed in nature, at least for a long time, because over time, the population may run out of space to live in. Over time, population may run out of food. Maybe there will be some disease that will spread at some point in time and kind of cut the population back and keep cutting it back, preventing this exponential growth to cause the population size to be infinite, basically. Did I answer your question, Samir? Oh, okay. I see your response. Ava asks, does the human population grow exponentially? Yeah, and I will talk about it in detail in a couple of slides from now. We're in very strong exponential growth, and it's kind of staggering when you look at the graph of it over centuries. But first, I'm going to kind of give a couple of examples of exponential growth and discuss it in more detail, exponential versus logistics. So exponential growth rate decreases over given time periods. And very important to remember that growth is exponential when resources are unlimited. So this is the graph of the population growth of the gray seal pups on an island in Nova Scotia in Canada. Okay, and here we see that the gray seals are not limited by the resources on that particular island. And that is why over 30 years, or rather 40 years of observations, almost 40 years of observations, the population size increased exponentially. The exponential, again, curve is characterized by a J shape. And this whenever you see an exponential growth in a population, the immediate piece of information that you should take from it is that nothing limits population growth. Okay, population feels very well in the given area. It's likely very healthy, and it's gonna, keep increasing in the future. Now, the exponential growth is unsustainable, though. Because the more individuals there are within a population, the more strain it puts on the resources of natural resources that population requires. So this kind of graph shows the rotifers. This kind of organism is called rotifers. The dynamics of the population of rotifers over time. So initially, the rotifers increase, the population of rotifers increases exponentially, but over time, they run out of physical space to exist and they start just dying out because of the overpopulation. So in this particular case, the carrying capacity is at 2,000 individuals sample per sample space, or rather volume of habitat, and the population stabilizes after at 2,000 individuals. Now, I want to, who's taking calculus here? Like, can you just raise your hand or drop in chat who has taken calculus? One person, two people, three people. Okay. So for those of you who did or didn't, I want to mention something. So if you've taken calculus, then I'll mention, you know what, I'll mention it for everybody. In exponential curve, in exponential growth rate, not only population size increases in exponential growth rate, but also the growth rate itself keeps increasing. So if we look at this graph where x-axis is time and y-axis is total population, we see that population size increases. Now, population growth rate also increases. And what is growth rate? It's basically the slopes of the tangent lines to the slopes of the lines that are tangent to this exponential curve. So in here, the slope will be small. In here, the slope will get larger. In here, in this section of the curve, the slope is even larger than here or here. So the slope of the tangent of the lines that are tangent to the curves increase, and that kind of illustrates why the population growth rate increases as well when population growth is exponential. I hope that made sense. I will not ask you about this. It's just kind of application of calculus to understanding of the exponential growth rate of population as well. And when I connected it in my head many years ago, it kind of made me feel good about myself. So I hope that that will make something click for you as well. So logistic growth slows and stops over given time periods. Every habitat has some carrying capacity, which is the maximum number of individuals that the habitat can support indefinitely. So if a population reaches this carrying capacity, it's said to be in a steady state. The population size will not decrease or it will not increase once it reaches the carrying capacity. So once the logistic curve here, again, has an exponential phase, and it has phase where the growth rates or the slopes of the tangent lines are slowing down once the population size approaches the carrying capacity. So if in this section of the curve where the growth rate is exponential, there's nothing limiting the population size and population reproductive rate. But once the population size approximates this carrying capacity, the growth rate gradually slows down and eventually reaches the carrying capacity. This kind of example is one of the possible outcomes. Sometimes the population size overshoots the carrying capacity, and then the individuals start dying out at an increased rate, and the growth kind of returns to the carrying capacity here. So this is kind of an ideal situation where nothing catastrophic happens to the individuals, but a lot of times in nature we see that the exponential growth overshoots the carrying capacity, and then the individuals start dying out, and the curve exponentially decreases and reaches the carrying capacity and remains stable. Alrighty. So The third type of population growth, or rather population dynamics, is going to be oscillatory. And oscillatory meaning fluctuating. Um, so oscillatory population, or I'm going to use fluctuating population dynamics, is the dynamics where the population growth is neither exponential nor logistic, or it basically fluctuates. And it's very characteristic for the populations that are for the prey population and the corresponding predator populations. So this graph shows the dynamics of the population of lemmings and stoats over time. So x-axis is years, this y-axis represents the lemming population, and this y-axis represents the it's a proxy for stoats, population of stoats who prey on lemmings. So the you see that the green curve is kind of fluctuating. So first the green curve increases, and which is population size of lemmings. And the stoats are getting very happy about that because there is lots of more food around. And because there's lots more food around, the population of stoats starts to increase as well. And note that the population of lemmings is kind of increases faster in here. And only after the population of lemmings increased, the population of stoats starts increasing as well. There's some lag between the increase of population of lemmings and stoats. And this lag is because of basically it takes time for the stoats to recognize the good conditions for more reproduction. Good conditions being the availability of food, availability of lemmings. But with time, the population of lemmings will be overhunted by stoats, and it will start decreasing. And after the population of the food decreased, the stoats population will start decreasing as well. And after a while, after the fall of the population of stoats, lemming starts reproducing well again because they're not hunted as intensively anymore, and the cycle continues. So this is the example that is given in the recommended book for this class, but another classic example that we've probably seen before is with snowshoe hares and lynx populations in Canada. It's very classical example that is given in education environment. And basically the it can be visualized with the same curve, and imagine the purple curve would represent snowshoe hares, and the green curve, oh, I'm sorry, vice versa. The green curve would represent the population of snowshoe hares, and the purple curve would represent the population of lynx. Okay, does this make sense? The why the populations fluctuate, and like what population would increase first, and which population would increase would be the dynamics of which population is secondary to the dynamics of the of which population, other population. Are you guys checked out? Are we still here? Are we still? Yeah. Okay, great. So many conditions limit the population size, many conditions that I've already touched upon, but I'll kind of give more structure to understanding them. Many conditions kind of contribute to the population size not being exponential, where population dynamics over time not being exponential, but logistic. So a combination of factors determines the size of most populations, and factors limiting population size might or might not depend on the density of the population. So there are two classes of factors that affect the population size. One class is basically is density dependent, and another class is density independent. And density, when I say density, I mean population density, the density of individuals within a population per unit of space. So density dependent factors, they usually biotic, meaning they're caused by they're biology related. They result from interactions with living organisms. So there is one of the density dependent factors that affects population size is competition for space, nutrients, food, or mates. Like when you consider, like imagine the forest stand. Within a forest stand, the younger trees have the highest probability of dying, and you'll notice that the young, if you go out and into a forest stand and kind of take a look at how dense are the big trees and the little trees, you'll notice that the little trees are much denser compared to the big trees. And at the same time, the mortality rate, the rate of death of the little trees is the highest within the forest stand. And that is because those little trees are competing for space. They're competing for sunlight with each other. And remember, the plants photosynthesize, they need sunlight to produce sugar, to convert CO2 into sugar and water into sugar. Um, what else? The little trees, they all, because they're spaced so closely together, they compete for nutrients. They need nitrogen from the soil. They need phosphorus from the soil. They need water from the soil. And this competition, it eventually results in the higher mortality rate because there's so much nutrients that is available. There's just so much water that is available to them. If we look at if we go back to the not life, but animal populations, uh, we also can think about spread of the disease as one of the density dependent factors that affects population size. The diseases spread more easily when individuals are more dense, with more densely spread within the population. So the higher number of individuals per unit of space, the higher the rate of spread of the diseases. Like if we don't have to like think of something that is too far fetched. Like imagine, remember the dynamics of spread of COVID within populations. The COVID spreads more easily in the cities compared to rural areas, and that's because people are communicating or like riding the public transport, or there are more people within any given store, which kind of promotes the easily, which promotes the rate of spread of the disease. Now, density independent factors that limit population at all densities, they are usually abiotic or caused by something non-living. One of the examples of the density independent factors that affects population size is fire. When the fire, uh, in the event of fire, fire basically kills trees, it kills animals, and it doesn't care how densely how dense was the population of animals or how dense was the population of trees. It's gonna once it's ignited, it's gonna burn everything. So other natural disasters that affect population size include floods and earthquakes. Some human-induced disturbances include oil spills and other industrial accidents, and as well as habitat destructions related to human activities like conversion of forests into agricultural land, into cropland, to grow food. It's we don't care, like people don't care how densely populated, how dense the vegetation is in the forest or how densely it's populated with animals. It's just gonna we're just gonna convert that land into cropland anyway. So yeah. Any questions about the difference between density dependent and density independent factors? Okay, moving on. Now, human population growth has been exponential. So consider two graphs. Okay, so this first graph is depicts the population size, human population size over the past 10,000 years, just over 10,000 years. So it's basically like compared to the current population size, like the population size that was 10,000 years ago was just, it looks like a flat curve because it wasn't a flat curve, by the way, it was steadily increasing, but the rate of increase was very, very slow. Which looks like a flat line, but if we magnify this region, we would see that population was still increasing. There were several interruptions in the population growth, and the big one was the bubonic plague, which happened in Middle Ages, and it basically halved the population size. If you look at this curve here, you will see that the population reduced to half of what it was pre-bubonic plague outbreak. But afterwards, we see that the population recovered and then some, because in what was it, in 2019, or 2018, the population size was 7.5 billion people. Now that's a lot of people. It's huge. We have a lot of people on planet Earth. But if we zoom in on the population size between 1800 and 2018, basically that's the last point here, we see that the growth of the human population continues to be exponential, and it doesn't look like it's slowing down very much. So growth rates, again, growth, it's important to understand that not only population size is increasing, its growth rate is increasing as well, or the slopes of the tangent lines, of the lines tangent to the curves, are increasing as well. So why is it increasing? Why do you think, guys? Why is why is human population increasing exponentially?
We're able to manufacture our environment to basically keep like where if we do become resource limited, we can find ways to become, not limited, like agriculture and automation and all of these things, just making it easier for us to live.
Okay. When does let me ask it this way: when does population increase? Look, think of about growth rate and death rate, or birth rate and death rate.
When there's not as many natural predators.
Sorry, go ahead, Madeline.
Oh, I said when there's not as many predators hunting the species.
Okay, good. Dylan, what were you saying?
I was literally just about to say our death rate has declined because of modern medicine, and the expectation of human beings' life has gone up a lot, and that is leading to a lot of people.
Uh-huh. Good. So what I was getting at is the population size increases when birth rate is higher than death rate. So birth rate has actually declined in a lot of countries, but death rates declined even faster. And most of the human population growth is attributed to basically declining death rates. And death rate declined drastically after the invention of antibiotics during the Second World War, I believe. And before the invention of antibiotics, most of human deaths were attributed to infections, bacterial infections and viral infections, in fact. But antibiotics didn't affect the viral infections. Vaccines did. Antibiotics kind of affected the death rates from the bacterial infections, which was pretty high. So the death rates declined drastically. Also, the inventions of modern medicine, such as vaccines, they also contributed to drastic declines in the death rate. So basically, modern medicine is responsible for the rapid decline in death rate, because we had agriculture. Agriculture was there since 8,000 BC, but it didn't. The population size didn't shoot up after agriculture. Now, industrial revolution affected the population growth, because during industrial revolution, people started basically manufacturing more things and living in cities, and like life became more comfortable, basically. And shortly after industrial revolution, we had major advances in modern medicine. Okay, I see a comment from William. With exception of natural disasters, we also control most of the density independent factors that would negatively affect us, right? What kind of density independent factors do you have in mind, William? William, can you give an example, like what kind of density independent factors you had in mind? The thought is interesting, and I want to know what you were thinking of. Okay, Leah must have stepped out. Well, chime in if you're here. Anel says technology helps us produce more kids as well as like IVF. Birth rates, I think from what I know, IVF kind of helps people move up the age when they had their first babies. Like women started working, and because of basically in delaying the age when they first have babies, and IVF kind of arose as a response to that because fertility declines with age, and IVF just kind of is an invention to help women have babies at older ages, from what I understand, like historically. Um, so Sydney says we have technology to stop and slow fires. We have systems to track hurricanes so people can be prepared. Fires are kind of a tricky thing. We don't. It's a. I would debate like whether humans have positively or like enhanced fires or suppressed fires. Yes, fire suppression efforts are large, but also when you suppress fires and not let fires happen in the ecosystems that are for which fire is just part of their natural process, part of their existence, you make fires more severe later on. For instance, in California, they have like bad fires, right? But these fires are so bad not only because of the changing climate, because of the conditions are becoming more dry, but also because of the fire suppression efforts. When the fire is suppressed, when fire is basically stopped from happening in the first place, then the kind of vegetation that basically develops in the area is more dense. It has more fuel in it. Okay, so once the fire actually happens as a result of a lightning or as a result of power related outages, the fire that happens as a result of that lightning is going to be more severe because there's more fuel for it to kind of catch on. Okay, so fire suppression is beneficial in the short term, I would say, but it's not beneficial in the long term because fire suppression often results in more catastrophic events when that fire does happen. Okay, there's a couple of more things that I want to cover here, so I'm just going to move on. Thanks, guys, for participating. Lots of interesting thoughts. So birth and death rates vary among human populations worldwide, and much of the current growth in human population is due to high birth rates and low death rates in less developed countries. So why is this happening is because in the developing countries, the advances of modern medicine have been lagging. So first, the death rates have decreased in the more developed countries because of the more developed medicine, but death rates in the less developed countries have not decreased until recently. So the low death rates in developing countries are like still a relatively novel thing. So to people, like if you consider individual families, uh, before before the modern medicine, before like modern stuff that would decrease your probability of death, people used to have a lot of kids. Okay, it wasn't uncommon for a family to have 10 kids, and people had a lot of kids to kind of increase the probability that they will have at least some kids left after 20 years or 30 years. And so kids unfortunately used to die a lot because of the infections and because of the developing immune system. So, but the modern medicine helps increases the chance of the survival of the babies. But in the developing countries, people are still in the mindset that we got to have a lot of kids in order for some of them to survive until puberty, or some of them to survive and help us out in the old age. But the medicine is there. So the technology is there to help decrease the death rates of childhood mortality, and people just they're creatures of habit, so they still have this culture of having more kids, and these kids eventually grow up and contribute to increasing population size in the developing countries. So in the developing countries, the death rates are low, but birth rates are still high. Whereas in more developed countries, which had medicine, which have been benefiting from the medicine for longer, their birth rates are low and the death rates are low. So age structures. Let's take a look at those for a bit. So here in this graph shows the age structures of three populations: population of India, populations of United States, and population of China. So the y-axis here represents the age classes of the individuals. So individuals from which aged from 0 to 4 years, from 15 to 19 years, and so on. Now, from these age structures, you can kind of tell whether the population of a given country will be increasing or decreasing. And it's important to kind of keep in mind that that conclusion can be made with an assumption that there is no emigration or immigration going on in the country, because that's kind of going to disrupt the age structure and the conclusions that we can make from the graph. Now, in India, most of the populations is most of the population is young. Okay, the reproductive years are considered to be between 15 and 50. Okay, so lots of individuals are young, and like let's say 20 years from now, these individuals over here, these individuals, males and females, all of these individuals will enter the reproductive years and make even more babies. Okay, so that is because there's lots of lots of children basically in India. The population of India is projected to be increasing in the future, because these guys will enter reproductive years and produce even more babies. Now, this kind of population age structure is said to keep population size stable, because there is approximately even proportion of individuals within a population in pre-reproductive years, reproductive years, and kind of old age. And this kind of age structure, which is characteristic for China right now, it is said to result in a decline in the population like 20 years from now. So 20 years from now, the population of China is projected to decline because there is like proportionately there's less babies that are than people that in the reproductive age right now. So this cohort, like 10 years from now, or 20 years from now, it will enter reproductive years, and it will produce like maybe the same amount of babies or even less. I haven't heard, like China used to have one-child policy aimed at decreasing population size, and that basically says that it's working. So I'm not sure whether they've lifted this one-child policy or not, but if it stays in place, this cohort will be halved, resulting in even more drastic population decrease.
I know a little bit about this. They've actually changed it to they're actually a two-child policy now.
Mm.
But one of the things that they're noticing is that because of the one-child policy doctrine that they had for so long, there's a continuing theme of families only choosing to have one child, even though the policy has changed. Like China is dealing with an after effect of their one-child policy. Like this was always going to happen.
That's interesting.
This mess was going to happen, and they kind of let it happen.
Yeah, well, it looks like China is going to encourage immigration. So if you're thinking of immigrating to China, maybe they'll, like, next 10 years is going to be a good time.
Yeah, no.
All right. What else did I want to say? It's 10:19. Okay. So I have 1 minute just to highlight the differences in the causes for mortality in different countries. So in high income countries, we tend to die from the heart disease, mainly resulting from coronary artery blockage, from strokes, from Alzheimer's disease. So top three causes of deaths in the developed country, in high income countries, I should say, are the diseases associated with old age and diet. Like number four is lung cancer, which is associated with smoking. And number five is COPD, chronic obstructive pulmonary disease, which also often results from smoking. So it's basically lifestyle and old age kind of diseases or causes of death. Whereas in low income countries, the number one cause of the disease is lower respiratory infections like pneumonia or acute bronchitis. And pneumonia is basically caused by bacteria, or there's viral pneumonia. But often viral pneumonia is kind of co-occurs with bacterial pneumonia, because bacteria are happy when virus is there, because it creates good conditions for them to spread as well in the lungs. Now, diarrhea is number two example. So basically, it's the top two causes of deaths in the low income countries are deaths that are preventable with the use of antibiotics. Okay, so in low income countries, top two causes of deaths are preventable, and basically they describe the lack of either access to medical services, or in some cases, quality of water, and maybe even education. Education in terms of like people don't necessarily know how to preserve food correctly, or how to basically maintain hygiene so that they don't infect themselves with something horrible. And number three cause of mortality is stroke and heart disease. And then number five is unfortunately HIV/AIDS. And it's 10:21. So are there any last minute questions before I stop the lecture? Okay, well, thanks for your participation, guys, and I'll see you on Friday.